Hey Royals, in this video we're going to analyze some Newton's laws, but in the case of these problems we're going to have to include friction. Okay, so there's a problem on our screen right now. The two boxes, box A and box B, being dragged towards the right with a force of 145 newtons. And they're connected with a rope. In the question we're asked to find the acceleration of the system, and we're asked to find the force that B applies on A. So let's start with a free body diagram. And I encourage you to draw three different free body diagrams here. One for box A, one for box B, and one for the combined system. Okay, so we'll start with our free body diagram, FBD of A. And if we drew that free body diagram of A, we have to think to ourselves, what forces are acting on A? Well, the fact that we are told about friction, and we're given a coefficient of friction, indicates that there's going to be an opposing force to the motion. So we'll call it FF, and we'll use the subscript A to indicate that that's the force of friction on box A. Now, there's a tension force pulling towards the right, and I'm going to say that that's FT. And in fact, that is caused by box B. So this force FT, we can say, is the force of B on A. So if we can determine the tension force on box A, that's the force that box B applies on it. Okay, so also we have that force of gravity pulling the box downwards. And because it's in contact with that horizontal surface, we have a normal force acting straight up in our case here. Now box B, let's draw a free body diagram for box B. FBD of B. And we'll do the same type of analysis. We'll draw ourselves a square here, and we will draw the normal force acting straight upwards from the surface. So it's perpendicular to the surface that we're dealing with here. There's force of gravity pulling box B downwards. Now we have that applied force. I'm going to call it applied, F applied, and we'll write APP for applied. And it's going to be a magnitude of 145 newtons towards the right. And we have this tension force acting backwards or opposing this applied force on box B. But box B also has friction applied on it. So we're going to say F friction on box B is also acting towards the left. Now, if we're looking for the acceleration, the easiest way to find this acceleration is to look at the combined system, or the system as a whole. So we actually have two boxes with a total mass of 45 kilograms being applied by a force of 145 newtons. And we have on this combined system some type of friction that is going to be acting to oppose this applied force. So what I want to do is I'm going to draw the free body diagram of the system. And when we do that, we have one single box. So I'm going to just draw it right in the middle here. We have one single box with a mass, and we'll find the mass of a system. We'll say it's the mass of A plus the mass of B. And so that gives us 10 kilograms, because that's the mass of A. We'll add it on with the mass of B, which is 35 kilograms. And we mentioned that we have 45 kilograms as our total system mass. Okay, so we have to ask ourselves, well, the fact that there's mass means that it's going to be attracted to the center of Earth, so there will be a force of gravity acting on it. Now, because it's in contact with a surface, we get a normal force. And I'm going to use the subscript S to represent that we are dealing with a system here. There's going to be a friction acting towards the left, and I'm going to call that the friction of the system. We have to think to ourselves, well, that friction of the system comes from the friction of box A and from the box B. So we'll have to determine the frictions of each individual box. And there's this, again, this applied force on our system, which is acting towards the right, and it's still 145 newtons. Okay, so this is the free body diagrams of each individual box and then the whole system. And how we're going to use this is we will use the system to find our acceleration. But the few things we want to do before we dive into that is that we want to find the friction forces on each individual box because of this total system friction. So let's start with finding the friction on box A. So from box A, we have to ask ourselves, well, friction has the equation force of friction is mu Fn. And I need to know what the normal force is. And we know normal force on box A comes from that vertical direction. So let's go ahead and analyze the vertical direction of box A. So we have the net force in the y direction. That's going to be our vertical force. Is going to be equal to m of box A multiplied by the acceleration of box A in that y direction. And that's a vector. And since the box is not accelerating off the surface, or it's not accelerating vertically at all, that tells us that this net force will be equal to 0. That's because the acceleration is 0. So we have that the net force in the y direction on box A, and I'll put a little a here to remind us that we're dealing with box A, has to come out to 0. Which means that the force of gravity acting on box A plus that normal force acting on box A have to come out to the value of 0. Well, the force of gravity on box A is then going to be equal to the negative of that normal force, and they're vectors. So that tells me that the normal force, and I'm just going to flip my equation around here, normal force is going to be, or the negative normal force, is equal to the mass of box A multiplied by our gravitational field intensity. And so we can say, all right, normal force on box A is equal to the mass, 10 kilograms, multiplied by 9.8 meters per second squared, and that's going to be downwards. And this is still negative. So that gives us a value for the normal force, or the negative normal force, of 98 newtons down. Well, we don't want the negative normal force, we want the normal force. So the normal force on box A, and this should still have a vector on it, will be the opposite direction. So 98 newtons acting upwards. Okay, and that's because I dealt with the fact of negative and the downward directions. So that should give us enough information that we can find the friction force on box A. So let's go ahead and do that. So the friction force on box A is equal to mu Fn. Now we now know what Fn on box A is. We also know the coefficient of friction, and the coefficient of friction in this problem is 0.25, and that was given to us at the bottom of our picture. So the coefficient of kinetic friction is 0.25, no units on our coefficient there, but it's multiplied by 98 newtons. And the direction, remember that this equation is only giving us a magnitude for the force of friction. It doesn't give us the direction, it just gives us the magnitude. And so we know that the force of friction on box A has to be the product of these two values. And if you multiply that, you get 24.5 newtons. Okay, so that tells us from analyzing the situation that this, if it were a vector, would be 24.5 newtons acting towards the left because it's trying to slow our box down. Okay, so let's do the same type of analysis, but this time for box B. Okay, so we're going to look at box B. So from box B, and remember we're going to look at the vertical direction to find the normal force first. And so I'm going to say F net on B in the y direction is equal to the mass of box B multiplied by its acceleration in that y direction. So acceleration of box B in the y direction. And once again, because the box is not moving vertically at all, it can't be accelerating vertically. And so that means our acceleration is 0. So we determine that the net force on box B, and this should have a vector on it, is that the normal force on box B plus the gravity force on box B has to come out to 0. So that means the normal force on box B has to be equal to the negative of that vector for gravity acting on box B. So the normal force acting on box B is going to be negative m mass of box B multiplied by our gravitational field intensity. Okay, so let's calculate this. Normal force vector negative, and our mass for box B was 35 kilograms. And we multiply by 9.8 meters per second squared downwards. All right, multiplying that through, we get a value of 300. So normal force on box B of negative 343 newtons, but that's downwards. Well, we have a negative and downwards, which means that that normal force better be pointing upwards, and that's what we expect, of 343 newtons, and it's going to be upwards. Perfect. So now that we know the normal force, let's tackle the force of friction acting on box B. So the force of friction acting on box B is going to be equal to the coefficient of kinetic friction multiplied by the normal force acting on box B. And so that tells us that the force of friction acting on box B is 0.25, because that's the coefficient of friction acting between the surface and box B, multiplied by this 343 newtons. That gives us the force of friction acting on box B of a value of 85.75 newtons. So we can put a direction with that. The force of friction on box B is going to be 85.75 newtons, and that acts towards the left. So Royals, we have two forces of friction here. We have the force of friction from box A, which had a magnitude of 24.5 towards the left, and we had the force of friction acting on box B of 85.75 newtons acting towards the left, which means that my total force of friction, so let's do this, the force of friction, oops, I want that to be capital, therefore F friction total is going to be the force of friction on box A plus the force of friction on box B. I'll zoom in here. We'll correct up that F so it looks like an actual F here. There we go. And so let's substitute our numbers there. We get that we had 24.5 newtons acting left from box A plus that 85.75 newtons for box B, which gives us a grand total for a total frictional force of 110.25 newtons acting left. So finally, we know what the force of friction is on our combined system. So if we go back to the free body diagram of our combined system here, so I'm just scrolling up, we now know this value of 110.25 newtons. So horizontally, we have a lot of information. We have that the frictional force acts towards the left with a certain magnitude of 110.25, and we have this applied force acting towards the right of 145 newtons. So the difference between those is going to attribute to an acceleration of our box towards the right. All right, so let's determine what exactly that acceleration is. Okay, so we're going to use our combined free body diagram from FBD of system. We have that the net force in the x direction must be equal to the mass of my system multiplied by the acceleration of the system. Okay, so x system. All right, so thinking back, we had an applied force on the system, and we had that frictional force on the system, both acting in the horizontal direction. That must come out to the mass of the system multiplied by the acceleration of the system. All right, the applied force was 145 newtons, and that was acting to the right. The frictional force was 110.25 newtons, and that was acting to the left. The mass of my system, which we calculated earlier, was 45 kilograms. And the only thing left here is the acceleration of our system in the x direction. Let's deal with the left-hand side here. Make sure my vector is in the right direction, 145 newtons. To the right, subtract 110 newtons, 110.25 newtons to the right is going to be equal to 45 kilograms multiplied by my acceleration in the x direction. All right, so that tells me that I get 34.75 newtons acting to the right is equal to 45 kilograms multiplied by the acceleration, again, in the x direction. Divide both sides of my equation by the mass, or the system mass, you get a value of 0.772 meters per second squared towards the right as my acceleration of the system in the x direction. So Royals, we just found our acceleration of our combined system, which means that that's the acceleration of box A and that's the acceleration of box B. And this is solely because the boxes are combined, and so whatever acceleration we find in the x direction is going to be the acceleration for both of these boxes. So 772 meters per second squared, and in fact it is towards the right. All right, so let's think about this. That dealt with this piece right here. We've now determined the acceleration. We want to find the force of B on A. So you can see that that tension force, which we said was the force of B on A, shows up twice. Probably the free body diagram that's easier to use is this one right here, this force free body diagram of box A. And so I'm going to take this picture, I'm going to duplicate it, I'm going to move it down. So I'm going to move it all the way down. Oh, let's do this one more time. Let's get rid of that. I'm going to duplicate that. I'm going to move it down to here. I'm going to keep moving it down on my page just so we can see it while we're working with it. There it is there. And so we want to determine the the force of box B on A. Okay, so if I look at that, I know the acceleration in the x direction of 0.772 meters per second squared. That's to the right. If I go back to my work earlier, I found that the force of friction on box A was 24.5 newtons, and it's to the left. So the only piece of information I don't know in that horizontal direction is this force of B on A, or the tension force. So we can say that F net in the x direction on box A has to be equal to the mass of A multiplied by its acceleration of in the x direction. So A in the x direction. So that tells us that F of B on A plus the force of friction on A is equal to the mass of A multiplied by its acceleration in the x direction. All right, so F of B on A, let's substitute in some values, plus 24.5 newtons acting to the left must be equal to 10 kilograms multiplied by this acceleration of 0.772 meters per second squared, and that's to the right. Okay, so that tells us B on A is plus 24.5 newtons to the left must be equal to 7.72 newtons to the right. Well, now let's deal with isolating for our unknown here. This is our unknown that we're trying to isolate for. So I'll subtract 24.5 newtons to the left from both sides, and that leaves me with 7.72 newtons towards the right. Subtract this 24.5 newtons to the left, and we don't like vectors in opposite directions, so that tells us that if we were to change the direction of our second force here, we get to the right added with 24.5 newtons to the right. So the force of B on A, based on our analysis here, has a grand total of 32.2 newtons towards the right. So this question asks us to find two things. It asks us to find the acceleration in the x direction of our system. So I'm going to say, therefore, A is equal to 77 meters per second squared towards the right, and the force of B on A is 32 newtons towards the right. Okay, so there we go. We've solved this problem. Again, if you have any questions or concerns about anything I've done in this lesson, please do not hesitate to reach out to me.